In this video, we would touch basic concepts of linking, which every programmer should know. For the purpose of this video, I would use Linux operating system linker. But same principles apply even if you use Windows, macOS, or any other operating system. You will hear words like lazy binding, PLT, ELF, relocation entries, and many more. One of the core concepts of computer science, which is hardly understood properly, is how linking works. You might ask, what is linking? In computer science, linking is the process of combining together different pieces of code and data spread across different files into a single file, which can then be loaded into computer's memory and eventually, after loading, executed. This is how applications are built and run. Usually, you build an executable out of source code and eventually execute it. Linker does a good portion of that work. In many applications, linker doesn't just work at build time, but also at runtime. Understanding linking would not just give you a deep insight into how programs run on a computer, but it would also help you resolve those frustrating and hard to find bugs in programs. It broadens your understanding of the whole operating system. If you are a programmer, I bet this knowledge would help you. We know already how to compile code and produce an executable. Usually, operating systems provide a single button in a UI or a single command to compile the whole project and produce an executable. Underneath that build process, you will find a compiler, for example, GCC on Linux. GCC command is not actually just a compiler, but a compiler driver. Because on Linux, when you run GCC, it's not just the compiler you run, even though it is just a single command. Underneath that runs preprocessor, compiler, assembler, linker to produce an executable or a library as end product. It takes code as input and gives us executable or final application as output. One of the important steps of the whole process is linking. To build an executable, linkers usually perform two main tasks. First would be symbol resolution, and then the second would be relocation. Before we dig deep into them, it would make sense for us to discuss some key concepts and of course sample code we would use in this video. Let's just quickly go through these two code snippets again in more detail. I just want to make sure that you remember the code snippet thoroughly. Main.c includes a header file and has a prototype definition of add_list_members function. Then we have a static array variable definition here, which has been initialized to an array with two elements. We have main function of the application here. It has local variable ret for storing return value from a function which calculates sum of all the numbers for the array for us. The function takes array and the number of elements in the array as input. In the end, we print the return value from the function. The return value is the sum. The function which does most of the work for us is in the file add.c. It just loops over the input array and adds all the numbers into a local variable and eventually returns to the caller. Pro C programmers will of course point out many issues with this example C program. It does not validate the input parameters and it does not work for all the inputs. It would of course overflow and underflow in many cases, but that is a topic for another time. Here we just want to demonstrate how linking works, and we just want to make sure that we understand the concepts which we need to get started. So to summarize, we have two types of files we are dealing with here: text files and object files. Text files are the files which we have all the source code in and are taken as input by the compiler driver. All other files, for example, intermediate files and final output files, are object files. Object files are stored in a format called ELF format. Commands which we are going to use to interpret these files are object dump and read ELF. Their sole function is to read object files in ELF format and show the information to us so that we can process it faster. So to use these tools, if you want help, you can always use man pages. For example, object dump, we will use options like disassemble to display the assembly for the machine instructions, or in simple terms, just disassemble the binary content. reloc option to print the relocation entries of the file, or source option to display source code intermixed with disassembly. Another useful tool is read ELF, and it can be used to print header files or different sections of ELF file. It also has a reloc option similar to object dump, which prints relocation entries. We will talk more about it soon. We now have add.c, main.c, and makefile here. Makefile here is to help us compile the code. Instead of trying to type in long commands, we have automated compilation process by writing this makefile. Let's compile the example source code, and as you can see, we have this no PIE option here to make sure address space randomization is disabled for us. This would help us explain details without randomizer throwing us off. Explanation of PIE or address space randomization is out of scope for this video. As you can see, 3 ELF files were generated by compilation, and these also include an application. While we are at it, let's also compile with debug info option -g, so that we have source code related information also in the final binary. You can see here we have 3 extra binaries with _d suffix. Using -g option to compiler, we generated them. This option is useful for putting debug information into ELF files for later stages. We have non-stripped binaries here. Non-stripped would mean that binaries have complete information including debug information, and they are not stripped. One of the intermediate files, main.o, is a relocatable object file. Application binary is a executable file, and we also have a special application _d file, which is also an executable file, but it also has additional debug information in it. Now with object dump command, let's read the assembler mnemonics for the machine instructions from the main.o file. This is useful for investigation many times, and in case you have an object file with debug information, you could even display source code intermixed with disassembly. You can see call to add _list _members turns to 3 instructions. First 2 are setting up the arguments to the function, and the last one is the call to the function. Similarly, you can see 3 printf calls and their corresponding code. This again is useful for development and integration investigation purposes. Let's see the code again in more detail. On line 4, we see the second argument to add _list _members is being set up in the register ESI, but the address value of this register is 0. And at link time, linker would have to relocate the reference to this array with the actual address of the array. In place of actual address, we have zeros right now. Same holds true for even printf arguments. The only argument to printf is string, but the intermediate object file doesn't have the real address but is zeroed out, and linker would actually need to resolve this at link time. Compiler and assembler does generate instructions for linker in the form of relocation entries in relocation section. Relocation entries have enough information for linker to resolve those, and they are saved in this special section. With read ELF command, we can actually list down all these relocation entries for main.o object file. As you can see, we have 8 relocation entries. We have first 2 for add _list _members function call, and the last 6 are for printf and puts function call. We would explain them in detail soon. Now with object dump command, you can actually intermix relocation entries with assembly to exactly map relocation entries with locations where they are needed. Another very useful command to have in Arsenal. Now let's see the final disassembly of the application, and as you can see, all references have been resolved and all zeros have been replaced with actual addresses. There are 3 types of object files. The first relocatable object file, second executable object file, and the last one shared object file. Relocatable object files are files which can be mixed with other relocatable object files at compile time, and they can be made into an executable file or even a shared library. Executable files are files which can be directly copied to computer's memory and executed. Shared files, on the other hand, are third type, which can be loaded into memory and linked dynamically at runtime or even at load time with other files. All three types of object files use ELF format to store their content. ELF stands for executable and linkable format. You might ask, what is the role of ELF format? Every file is a set of bytes on the disk or in memory. The information stored on the file can be interpreted based on some encoding. For relocatable object files, even executable files or shared libraries, or even core dumps, this encoding is provided by ELF format. Different operating systems use different encodings, but concepts underneath are same. So what is the basic structure of this encoding? At top of the ELF header, which allows us to read the rest of the file and interpret it, it stores the magic number, the class, endianness, ELF version, location, size of section headers, and if available, even segments. The machine code of the compiled file is stored in text segment. Initialized global and static variables are stored in data segment. Uninitialized global and static variables are stored in BSS section. SymTab section has symbol table which stores all defined and referenced functions and global variables. There are many additional sections here and you can find useful documentation online about those. There are generally two categories of files in this format. First one is object files, which are broken down into many sections, and there's a section header table stored somewhere in the file which helps us locate those sections. We also call this linker view of the ELF file. Another category is executable format. In addition to sections and section header table, this format also has segment header table. Segment header table divides the file into segments which can be loaded at specific location in the memory. If we try to list down all the segments in an object file, we'll get nothing because object file doesn't have segments. It just has sections. But if we try to list down all the segments of an executable, we will get all the segments and we will also get a mapping between those segments and sections, which will tell us which sections this segment maps into the memory. As soon as we compile object files out of source code, linking view is useful. Linker uses linking view, that is sections for symbol resolution and symbol relocation, to generate final application and adds a segment header at the top. Segment header table is also called physical header table. Now let's run the application with GDB and put a breakpoint in the main function. Let's search the process ID for the application process, and then let's try to print virtual addresses in which executable was loaded. And let's then compare this to values we did just read using readelf segment command. As you can see, the value do match up, and so do permissions. Same information won't make sense for an object file, which is never loaded into the memory. Local variables inside a function are allocated on stack, but everything else, including global variables, functions, static variables inside a function or static variable outside a function, have a symbol in the context of linking process. On the basis of how linking is done, these symbols can be categorized in three groups. First one would be global symbols, which are provided by the object file. Second group is global symbols, which are consumed by the object file. And the last group is local symbols, which are defined and referenced by the object file itself, but are not provided for external consumption. Let's look at these three examples. We have three global variables and three static variables which are local to the file but are not available for consumption to the outside world. Now the first group has one initialized variable, one initialized to 0, and the last one initialized to non-zero. So does the second group. From the symbol table, we can see that three global symbols belong to either section 4 or section 3. Those who are uninitialized or initialized to 0 have been put in BSS section, and those initialized to something have been put in data section. Same holds for static variables which are local in the function. Let's go back to source code. There are 4 functions here: foo1, foo2, foo3, foo4. First 3 are global and all of them have static variable with name x. Let's see how this situation is handled in symbol table. We see that x variable has been renamed by appending a numeric value at the end to differentiate them. The value in value is an offset to text section to those values. Also, see the static function foo4. It is missing from the symbol table. All these symbols are created or exported by compiler for linker to help it perform its function. Assembler just then creates the symbol table using this information. For each symbol, symbol table stores name, type, binding, section information, value, and size. There are 3 pseudo sections which are also part of symbol table usually. These are absolute, ABS, undef, common. ABS is used for symbols which have absolute value and can't be changed by relocation. Here it stores name of file which produce this object file. Undef is useful for symbols which are defined elsewhere and used in this object file. Common pseudo section, on the other hand, is present only for backward compatibility with old source files that did not use extern. GCC was up until recently using this section to store global uninitialized variables. We have foo.c, bar.c here. Both have global variables with same name x. Foo.c here is the entry point for the application. That is, it has the main function in it. And it modifies variable x to 99. Then calls function f from bar.c. Eventually, it prints value x. Looking at the function in bar.c, from looks of it, it looks like f function would modify the global variable. The global variable has the same name, but in reality with old GCC, both variables with same name would have same location in memory, and modifying one would impact another. Static libraries and statically built executables have 2 major disadvantages. As you might guess, all software needs maintenance, not just important updates, but security updates as well. Once applications are statically built, it's not possible to link to updated library automatically. It has to be linked again with library and reloaded. Even bigger disadvantage is, of course, that static library code duplication happens in multiple processes because it was copied into final executable at link time. And you can imagine with hundreds of processes running in a system, common libraries would be duplicated all over the memory in virtual address space of many processes. Shared libraries try to address these 2 disadvantages of static libraries. Shared libraries are built so that they can be loaded into any location in memory, and they are linked fully or partially either at link time or runtime. The program which does the job is called dynamic linker. The whole process is called dynamic linking. On Linux, these libraries have special extension .so, and on Microsoft operating system, they are referred to as DLLs or dynamic link libraries. Both shared libraries and executables can be loaded into memory, but shared libraries don't have to be at a single location. They can be anywhere, and they do not have any entry point. They just provide set of functions which multiple processes can link to. Both are, of course, ELF format files. There is a flag in ELF header which marks whether a file is executable or shared object file. ELF format sets aside a region usually outside the code. The code refers to this section when it needs an external symbol. The dynamic linker then updates this region every time it resolves a reference. The area is called Global Offset Table, or GOT in short. It usually lives in a section called .got in ELF format. Here we have a simple library code which refers to an I variable defined somewhere else. You can see at offset 1004 in hex, Inside text section, we have a move instruction computing the address of location I. It computes offset 3FF8 from start of the library, and that location is the location of global offset table. It stores 99 in a location pointed by that address stored in global offset table at instruction 11100B with move-L instruction. At runtime, dynamic linker would update the address stored in 3FF8 location using relocation type RX64 glob dot. This type means that to get address, you add base address with symbol value, which is 0 here, and on top add addendum, which is also 0. I hope this example makes the idea of GOT clear. Now, libraries usually contain many functions, and an application might be using only few of those. Depending upon the code flow and input to program, it might selectively call some of the functions at runtime and not others. This might even vary depending case by case or from time to time. But if dynamic linker has to make sure that all references are resolved while loading, we might actually be wasting its bandwidth if eventually none of those functions get ever called. What I mean by saying that is that resolving all symbols synchronously at load time in one go has many disadvantages. The cost is huge and the benefit might be far below the expectation, as application or caller might not eventually use any of those functions or just few of those functions. That is when PLT comes into play. ELF format has kept aside a section called PLT, or procedure linker lookup table, which helps dynamic linker to implement what is called lazy binding. Normal binding or resolution of symbols and relocation of symbols was synchronous up until now, but PLT helps it to be done only on demand. Once application figures out that it needs a symbol, dynamic linker would resolve it, and only at that time, not before. This might in turn mean that first time the symbol is resolved, the cost is high, and that is because dynamic linker might have to load the library into memory. All subsequent calls to the same function would be very fast because the address is stored already in GOT table after the first call. In some applications, the gain is huge because overhead of resolving all symbols has been avoided at the start. Let's go back to the terminal. We have our main function with few printf calls. It would become soon clear what print@PLT means. Let's list down all the dynamic relocations dynamic linker must resolve before or during execution of application. By default, modern Linux operating systems have lazy binding enabled. So every application would have a PLT section to which all calls to external functions would go first. You can imagine that every call you make in your code to an external function is replaced by a new function which is just a wrapper and calls that external function on your behalf. This wrapper function is placed in PLT table as an entry. So in this code, all calls to printf eventually go to an entry in PLT table. This can be clearly seen in the disassembled code of PLT section. In every PLT section, we have 3 instructions in total. First one is jump to global offset table. As soon as program reaches to the printf function, it jumps to the PLT entry. From PLT entry, the first location jumps to the GOT location. We can demonstrate this via GDB session of the application. Let's put a break at the main function. After disassembling main function, you can see we have just been waiting before printf call. Let's disassemble the PLT entry to which this call instruction jumps to. The first instruction of PLT entry has a jump instruction. This jump instruction reads an entry from GOT table and uses the stored value as destination for the jump. Look at the address value. It is stored in the GOT table entry. Let's see what that location is. Printing the GOT entry for address, it seems the location is next instruction in PLT itself. It might seem useless to jump between PLT to GOT and then back to PLT. Let me try to explain why it is useful. Once the code is back to PLT entry and in second instruction, a numeric value is pushed to the stack. And after that, another jump instruction takes code to another place. This location is actually a dynamic linker location, and the first push on the stack is one of the arguments to the dynamic linker. Dynamic linker would load the library into process's address space, call the function on application's behalf, and before returning back, it would update the GOT entry which pointed back to the second instruction of the PLT. It will update it to the actual address of the printf function. We can check with GDB session that the address value inside the GOT has indeed changed. This would make sure that next time printf is called, first jump instruction in PLT entry would take us to printf function directly without doing this dance between PLT and GOT. We can validate this by disassembling the new address in GOT. It indeed looks like printf function from library. The overhead of new call is very low. This is how lazy binding works. With this, we conclude our one-on-one session about linking. Thank you.